Okay, so today we'll continue studying both property T and amenability. Maybe we'll start with random walks. We'll give yet another definition of property T using random walk operator, and then we'll move to cohomological definition of property T. So somehow we'll see that also as far as property T is concerned, there are many definitions touching upon different fields of mathematics where we obtain equally very short characterizations of this property. And we'll do in a parallel way to definitions concerning amenability. So we'll start with this with random walks. This time in arbitrary Hilbert space. So the setting, as always, is that we deal with a finitely generated group. And now we can say that this is really the right setting. We've seen for the amenability that being amenable group is equivalent to the fact that every finitely generated subgroup is amenable. So indeed we can restrict our attention to finitely generated groups. And as far as property T is concerned, also we've seen that for countable groups, groups with property T are necessarily finitely generated. Okay, so now we see that it's not really restrictive to consider finitely generated groups if we talk about both amenability and property T. So now we'll consider unitary representation of the group gamma. So it's a homomorphism from gamma into unitary operators on some Hilbert space. And the random walk operator will be defined as follows. So if for any element in the Hilbert space, MV will be equal to the sum of the translations of this vector V by generators, okay, and will divide by the number of generators. And in order to have to be able to develop similar theory as in the case of when we talk about amenability expanders, we'll suppose that a set will always, sets S will all be symmetric. Whenever you have an element in S, you will also have its inverse, right? So when we talk about left regular representation, we actually argued that it should be called Markov operator, random walk operator. We've seen this interpretation with the return probability when we were talking about the spectral radius, right, of this operator. So indeed, here we can say that we have a random walk on the Hilbert space, where we're choosing one of the images of V by pi of S with equal probability 1 over the size of S. And now we can give the following characterization of property T. So the theorem will be that, well, if we are in the setting that gamma is a finitely generated group, we consider a finite symmetric set of generators. Group gamma has Kazhdan's property T if and only if the norm of this random walk operator M is strictly less than 1 for every pi, which is a unitary representation with no invariant vectors, non-trivial invariant vectors. Okay, and actually we don't have to give a proof of this theorem. It follows easily from what we've seen before, because we understood that norm being 1 is equivalent to having this almost invariant vectors. Okay, so indeed it right. So indeed it follows from the just spectral theory that, well, if the norm is equal to 1, we have almost invariant vectors, and of course if you have almost invariant vectors, the norm is equal to 1.
For P,
P, any for every unitary representation with no invariant vectors. Okay, and actually, so here this norm is strictly less than 1. Also, if we take the supremum over such norm of this operator over all unitary representation with no invariant vectors, it will be strictly less than 1. Okay, so this characterization actually gives us some numerical invariant related to property T, given a set of generators. If a group has property T, we obtain this non-trivial invariant. The supremum of the norm of this random walk operator over all random walks over all unitary representation with no invariant vectors in all Hilbert spaces. Okay, and that's an exercise for you actually to relate this invariant to some consequences of property T we've seen already, like for instance being family of expanders. Okay, we ask about the some non-trivial bound for the isoperimetric constant for this for expanders you obtain using property T, and indeed if you can compute or estimate, give a non-trivial bound on the norm of this operator, you also get information about this expansion. Okay, maybe some point we will talk more about this. It's actually quite interesting. This analytic invariant and this and relation with this more geometric invariant, which is the isoperimetric constant. Okay, so we might have time to go back to it and say more. Okay, so it's yet another characterization of property T, and also very similar to the one we've seen in the case of amenability, when amenability was equivalent to the fact that this norm is equal to 1. Okay, just for one unitary representation, left regular representation. Okay, so here you also see that these properties are are disjoint for infinite groups. Okay, and when we talk about, so somehow in these classes we talk in a parallel way about these two properties, amenability and property T. We know that they are opposite, but sometimes we obtain just the consequences of these properties, like with the with finite quotients of a group with property T. Last time we've seen that we can always obtain a family of expanders, right? Taking any family of finite quotient of group with property T will give us expanders. We said it's not a characterization, it's just a consequence of property T. And in a parallel way, we can obtain the similar result concerning amenable groups. So this time, if we have a finitely generated group, okay, okay, let us always, in different definitions, we are supposing that it's a symmetric set, like definition of a Cayley graph. And let gamma n be finite quotients of gamma. Okay, so and what we want to say that if gamma is amenable, it won't be a characterization of amenability, but a consequence that if gamma is amenable, then we will never get expanders. Okay, so then the isoperimetric constant of Cayley graphs of these finite quotients with respect to this set of generators S, yeah, we're taking the image of this generating set in this finite quotient, then this isoperimetric constants will tend to 0, necessarily tend to 0, if the size of this quotient tends to infinity. Okay, so with property T, we would always get expanders. With amenable groups, we'll never get expanders. Okay, so this is yet another instance of these properties being opposite to each other. Okay, so later we'll go back to it, but you can actually start to think how to prove it. But now we'll give a cohomological definition of property T, also very simple, very short characterization of property T. So we'll talk about cohomology of groups. Okay, with coefficients in Hilbert space. So we will consider a group gamma, which will be countable. Okay, we'll say the elements of the group gamma, let us denote it by gamma 1, gamma 2, gamma 3, and so on. And we'll consider a unitary representation of gamma. So we have this homomorphism from gamma into a group of unitary operators on some Hilbert space H. Okay, this will be a unitary representation. And in order to define cohomology, we'll have to define the space of cochains. So nth cochains of gamma with coefficients in this unitary representation pi, we'll define it as follows. So this will be the functions from n-dimensional simplices, okay, with values in this Hilbert space. So for us, as n-dimensional simplex will be n+1 tuple of elements in this group. Okay, so it will be gamma. It will be j not j n. Okay, j I. It's ordered n+1 tuple. So j I are in H. Okay, and as usual, we'll suppose that whenever we change the order, okay, so that we apply, say, maybe so maybe let us denote this simplex by delta. Okay, so this is this n-dimensional simplices, and whenever we change the order, so that we apply a permutation sigma to this simplex, so f of this will be equal to f of delta if we multiply by the sign of this permutation. Okay, so here this sigma is an element in the symmetric group on n+1 letters, and delta is n-dimensional simplex. But the really important condition is the equivariance, so that f of sigma, if we translate all the vertices of this simplex by g, so f of g sigma, it will be equal to pi of g f of sigma. Okay, so this is right. This is the definition of the space of cochains of dimension n. Okay, and now the definition of the.
G is the element of.
So this is true for every g in gamma. Okay, and now the coboundary operator, it will be the usual from Cn to Cn plus 1 is the usual coboundary operator. I hope that you don't mind that I won't use any more gamma and pi. Of course, this one should always write Cn of gamma pi. Okay, so then df of g naught gn plus 1, okay, it will be the sum of f of g naught, we omit the gi coordinate, gn plus 1, and its alternating sum minus I minus 1 to the power I. Okay. And one can check that indeed d is equal to 0. Okay, so first one have to check that the image is indeed in Cn plus 1, that we see we have this equivariance condition, and that that d square is equal to 0. Okay, so in this way we can define cohomology groups.
What is written in the definition of f of that is equal to?
So here we change the order of the vertices, orientation, and this is the sign of this permutation.
So this is identity for f, yes? That for all delta we have this.
So these are conditions that, so if you want, you defined f, if you have one order, okay, and then for any other order, it's defined by this formula, okay? And also, you have this equivariance condition, so it's indeed enough to define the value of f just on one simplex, which is in the orbit of the group gamma.
G is an element of H.
So G is in gamma,
On the right.
and this is an element in the Hilbert space H.
And G delta is translation on G, yes?
And this is right, G of delta. What does it mean? So delta is n plus 1 tuple, and when we write G, it means that we multiply by G, each coordinate. Each coordinate, right.
T of G, yes?
Sorry?
By T of G.
No, so here we multiply by G, the coordinates, okay? These are right. And here, because f of delta, its value is in H, so we apply pi of G to this element in H.
Translation on element G.
G0 is an element of what?
G0, G naught, these are elements, oh, thank you very much. These are elements in gamma, of course. Thank you. Thank you.
And differential, what about
Okay, and this is this alternating sum. Okay, very well. So now we can define the space of cocycles and coboundaries. So the space of nth cocycles, this is the kernel of D from Cn to Cn plus 1. Okay, and the space of coboundaries, this is the image by D of Cn minus 1, okay, in Cn.
And one question. Equivariant condition is including in the definition of
Right.
Yes?
Right. So the definition cohomological is that we included this condition in the definition of cochains. Okay, so it doesn't with this definition it does not appear in the definition of D operator. Okay, D is the standard operator. We chosen to include it into definition of cochains. Okay, and now we can define the nth group of, of cohomologies as the quotient of Zn by Bn. Okay, and what we would like to prove is the following characterization of property T. Okay, so we prove that gamma has property T if and only if the first cohomology group of gamma is 0 if we consider coefficients in any unitary representation. Okay, so this is yet another very simple characterization of property T. Okay. Before we will start talking about the proof of this characterization of property T, we'll try to understand the space of 1 cocycles and 1 coboundaries in this setting. Okay, so if we have 1 cocycle, okay, we said that it's.
We are proving the theorem, yes?
Yes, we will talk about the proof of this theorem. However, before doing this, I want to give another description of coboundaries on 1 coboundaries and 1 cocycles. Okay, that it will make easier discussion about this characterization. Okay, so we said that actually f. If we look at so f is defined on the couples of elements in gamma, but with this equivariance definition, actually it's enough to define it, say, on identity on elements of the form of the couples of the form identity G. Okay, any couple is in the orbit of such points, so we can actually so any cocycle is actually given by a function from G into from gamma into H, which corresponds to the value of f at identity G. Okay. So now let us look at the description of one cocycle. What does it mean that such a function is in the kernel? Okay, so we have to if we have f in C1, let us compute df at, so we set at G0, G1, G2. We'll try to understand what it means that this is equal to 0. Okay, so by definition of the D operator, this will be f of G1, G2 minus f of G0, G2 plus f of G0, G2. Okay. G1, yes, thank you very much. Okay, and now we want to, we said that it's enough to understand, we want to, at the end, to get to function which is on the couple identity G. So this is equal to, if you want to have identity here, we'll use the translation by G1 inverse. So by equivariance, this is pi of G1 inverse, f of identity
Maybe without
inverse. Yes, thank you. Right, but how, here we'll have to give inverse G1 inverse G2. Okay.
And here, excuse me, we may write G1 to the -1 both on the left or on the right side.
We will, no, we will, so here I'm using, maybe here it should be written, it will be on the left, right, and I hope we won't make a mistake, so please be careful. It's pi of G0, f of identity G0 inverse G2, and plus pi of G0, f of identity G0 inverse G1. Okay, very well. So here we have twice pi of G0, so let us write it as pi of G0, and then we are left with pi of G0 inverse G1, okay, say, right, f bar of G1 inverse G2, right, minus f bar of G0 inverse G2 plus f bar of G0 inverse G1, right? And we know that all this is equal to 0, and of course it's equivalent to being in the kernel, right? It's we can if we have this condition, we also obtain it's equivalent to this condition. So excellent. Okay, so we will actually maybe, so let us call it gamma, or maybe okay, let us call it gamma. If we call this, okay, maybe I write this condition, f bar of G0 inverse G2 is equal to f of f bar of G0 inverse G1 plus pi of G0 inverse G1 f bar of G1 inverse G2. Okay, and now I will call, if we call this H1, and if we call this, so this is H1, and this we call H2. Okay, so here we have element of the group H1, and here we have the element which is the product of H1 and H2, right? So what we've just did is description of the space of cocycles, cocycles as functions from gamma into H, which satisfy the cocycle equation. So namely that f of H1, H2 is equal to f of H1 plus pi of H1 f of H2. Okay, and this is true for all elements H1 and H2 in the group gamma. Okay, so one cocycles are the functions on the group gamma which satisfy this equation.
So we forgot about that it was defined on two-dimensional.
So once again, so this was
I understand, but we forget about that function. Yes.
Right. So you can from this from f, which was defined on one simplices, okay, and was in the kernel of the operator, we obtain such function, and vice versa. From such a function, you can go back to one cocycle defined described in this language. Okay, so this is equivalent another description of this space. Now maybe we'll give. Now we want to understand what are the coboundaries. Okay, so for the coboundaries, again, we want to give a description of the space of one coboundaries as function of gamma with some property. So we want to understand what it means in this language to be the image by D of C naught. Okay, very good. So we want to understand what is D F at the element G naught G1, when then we will take as G naught the identity. Okay, so df at G naught G1, this is f at G1 minus f at G0. Okay, so and
F0 кочеин есть?
Sorry?
F0 кочеин есть?
F, right? F belongs, so here F is in C naught, and we want to understand what is df. Okay, so, and we write now this using
C0 is a one parameter space. F is defined by its value.
Right. So f in C naught. This is an element in the yeah, it takes value in the Hilbert space, and it's defined for every element in the group. Okay,
And
but
it's defined by its value at identity.
But as we said, yeah, because of the equivariance, it's enough actually to do it for the at identity. Okay, so indeed, what we are interested in it's df at identity. Say now instead of g1, we'll call it just g. So this is f of g minus f at identity, okay, and by equivariance this is pi of g f at identity minus f at identity, okay. Now f at identity, well, as we said, it's an element of this Hilbert space, yeah, so let us actually call it v. It's a vector in the Hilbert space. So any element in B1 can be described as a function on the group G with values in H, which is of the form pi of G V minus V. Okay, so with this description, the one coboundaries are the functions from gamma into H, for which there is a vector V such that f of G is equal to pi G V minus V. Okay, so so indeed, well, the function which is of this form satisfies also this. So indeed, this is the subspace, and the characterization, this cohomological characterization of property T, tells us that we have a group with property T only in the case if every cocycle is actually of this form. Okay, that for every cocycle there exists a vector with this property. Okay, very well. So maybe after a short break we will talk about this theorem. So we'll discuss different aspects. Maybe what is always, so that you will have time a little bit to think about this, that we were talking, whenever we were talking about so far about definitions of property T, this we were considering given unitary representation, and we are looking about different like consequences. Like we're talking, for instance, about this. Consequences of this representation having almost invariant vectors. What would it mean in the different language, right? Yes. We started just so that we mentioned example we've seen today about this random walk operator. So this was translation, the fact that the norm of M is equal to 1. It was equivalent to having this almost invariant vectors in this representations. Okay, so we were really translating this property of having almost invariant vectors for a given representation to different characterization, to different contexts. Here, the situation is slightly different. Okay, we won't say that if we have for a given representation, this having almost invariant vectors implying invariant vectors is equivalent to H1 vanishing for this representation. Okay, here it's different. So actually what we'll show is that H1 being 0 implies property T, and this will be really for like we work with a given representation, and we'll get this characterization with almost invariant vectors for this of property T with this representation. However, if you want to prove that for group with property T, H1 vanishes, you have to use property T for all unitary representations. So there is something interesting, something deep in this characterization, and with this respect, it's very different from from what we've seen, characterization we've seen so far. So let us talk about this characterization. And actually, the proof we will see will show equivalence between property T and yet another condition concerning H1, where we need to introduce the not norm, but the metric on this linear space Z1. Okay, so the characterization we'll see will not be like algebraic here. So this is just saying that B1 is equal to Z1, but the one we'll see is that B1 is a closed subspace of Z1. So we just need to define the metric on Z1. Okay, so we can do this also on cochains, but so we will define the metric on the space of function of gamma with values in H, and it will be defined as follows. So if gamma is a, well, we already suppose it's a countable group, so we'll define first of all for two elements in two cocycles, we'll define it's the distance between F1 and F2, first of all taking into account only first n elements, so let us denote it nth, which will be just a pseudo metric. It might be equal 0 from different elements in Z1. So this will be just the, say, maximum between it will be the maximum of F1 gamma I minus F2 gamma I. This is this is the norm in this Hilbert space H. Maybe let us write it to be sure. And we take here the maximum over the first n elements in the group gamma. Okay, so this is distance, and now we can define the distance. Okay, it won't be a norm. The distance between F1 and F2 as the sum, when we will take into account this for all for all n's. So we take f1 minus f2, the maximum over the first n elements in the group. Here we will take the, we want to bound it by 1. We'll take, so we take the minimum of this number and 1. Okay, we cut it, we cut this at 1. And in order to be summable, we'll sum it with the coefficients like, so it will be 2 to the power minus n. Okay, so it's not the norm, but this is, it's a metric on Z1. And what is important, that it's a closed, it's a complete metric space. So in order to do this, you have to check that if you consider the sequence of functions satisfying this relation, converging to the function with respect to this distance, the limit function will also satisfy this condition. Okay, and this is obvious, yeah, that this condition is to the limit. So Z1 is linear space, and it's complete with respect to this distance. So this is called linear space, which is complete but not with respect to the norm, but some distance. It's called Frechet space. Okay, so Z1 is a Frechet space. And the characterization of property T that we're going to prove is the following one.
May I ask a question? Does the topology that induced by these distances pointwise convergence topology?
Right, so it will be a pointwise convergence, right. So the theorem will be that we have property T if and only if. So yeah, Z1 is a Frechet space, and we have this subspace B1 for every unitary representation, and property T is equivalent to B1 being a closed subspace. Okay, if and only if B1 is closed in Z1 for every unitary pi. Okay, say with no invariant vectors. Okay. And here we won't change representation. Okay, we will have this being closed exactly, which means that we don't have this almost invariant vectors for the same phi with no invariant non-trivial vectors. And in the previous, and here it's B1 equal to Z1. Okay, so this is stronger.
Without fixed vector.
Right. So.
There no condition.
Right.
And another question. Here we used the fact that our group is countable, and in the previous theorem.
Yes. So all this description I gave was for countable groups, right?
The construction works for uncountable groups. We can tell the story for the uncountable group. Yes.
So.
Define.
Yeah. So the whole lecture is just not only countable, but for finitely generated groups. Okay, we've seen that this is this is of our interest. So here the whole theory we're seeing is for countable groups. Okay, so with property T, there was only one point when we talk about locally compact groups. Okay, we wanted to say about property T for Lie groups. So this was just a part. You should consider this really a side in order to have to prove to say something about the way to prove property T. But otherwise, all the time we're talking about we're talking about countable groups. Okay, so this is all for countable groups.
But suppose we have an uncountable group, and we know that the right-hand side of theorem is true. Can we say that the left-hand side of the theorem is also true, or it doesn't work?
So here, like you will see the group, you will see the proof, right? So
here we use the metric and the fact that our group is countable.
Yes, right.
There we didn't use it.
Right.
So we can ask about this question about
right. But however, really the proof uses this definition. Okay, we will. It's true that we will stop. Stop here, at least today. I could then describe you this this condition. So once we've seen the proof of this theorem, okay, it will give us this implication that H1 being 0 implies property T. Okay, and as we said, if we want to prove the other direction, we have to change representation. Of course, this could be, so at some point we have to make a decision what we want to say, what we want to see in this class. Okay. All right, but so let us see the proof of this characterization. Right, so we want to prove that if we consider a unitary representation with no invariant vectors, having almost invariant vectors is equivalent to B1 not being a closed subspace. Okay, so the proof. Okay, so we consider, so we have pi with no non-zero invariant vectors. Okay, and we having so if we look at the application from H to Z1, which to every vector V associates an element in Z1, which is of this form. Okay, so it's a function f of g, which is equal to pi of g v minus v. Yeah, it gives us one cocycle, and because and this application is continuous, yeah? This application is continuous, yeah? It's very easy to check. It's continuous, and it's one-to-one. Why? Because being one-to-one means exactly that there are no invariant vectors. There are no invariant vectors. Okay. If we had two vectors which would give the same cocycles, okay, the same coboundaries, the difference would be equal to zero. Would mean that the difference of these two vectors is an invariant vector. Okay. Now, so this would be, so if we denoted this function f, actually denoted if we denote this application f, capital F, it means that there is f inverse. Yeah, there is f inverse from. So this is exactly the space of. This is exactly the space of coboundaries from B1 onto H. Okay. Now. Okay, now so suppose there are almost invariant vectors. Okay, there are almost invariant vectors. What does it mean?
Zero.
There are almost invariant vectors for this representation pi. Okay, so it means there is a sequence. There is a sequence vectors vi in H, say of norm 1, such that if you consider the sequence of cocycles of coboundaries associated to these vertiters, so that f of v, okay, f of vi, yeah, it is one cocycle, one coboundary. The sorry?
They should converge to 0.
Yes, with respect to this distance. Okay, so the distance between this and the 0 cocycle will tend to 0. Okay, this is exactly what it means to have almost invariant vectors. Okay, so it means that f inverse is not continuous, right? Okay, we have this linear map which is continuous, but its inverse is not continuous. Okay, but now if B were if B1 were closed, it would be a Frechet space, and F inverse should be continuous. Okay, excellent. So we've seen that if we have almost invariant vectors, if we don't have property T, then B is not a closed subspace. Right. That it's so I think it's like this theorem you probably seen in the case of Banach spaces, but if you go over the proof, or maybe you were fortunate actually to see it, you don't have to suppose that you have a norm. It's enough to have metric. Okay.
Sequence of semi-norms.
Right. Exactly. So these were, yeah, excellent. Okay. So exactly, we had this semi-norms and right. Okay. Excellent. So that's how you prove it. Okay. So for the so for the remaining time, maybe I'll discuss some consequences of this cohomological characterization of property T, which actually were considered for a long time to be very abstract characterizations, but nowadays one can use them to prove property T. So the theorem that we'll discuss now is the following characterization of property T. So the group gamma has property T if and only if every action by isometries on a Hilbert space, on Hilbert spaces, has a fixed point. Okay, so very nice characterization of groups with property T. Okay. By the way, this indication that we have the fact that we have so many very in different contexts such short characterization of property T, it's indication that it's a very important central fundamental property. Okay, so here we'll see that it is just change of the language. Okay, we have to translate our description of we'll have translate the actions on Hilbert spaces into the language of cocycles and coboundaries. Okay, so what is the action by isometry? So it means that we have homomorphism from gamma into the group of isometries of a Hilbert space H. So to every element G in gamma, we associate an isometry on H, and well, the isometry is described by the unitary part and by translation, right? So any isometry is of the form pi of G, okay? Pi is, so pi of G is a unitary operator on H, plus this translation part, f of G, okay? F of G is an element in H, okay? So what does it mean that this is homomorphism? Okay, let us write the relation that it's homomorphism. It means that if we have this isometry for the product G1, G2, so pi of G1, G2 plus this translation f of G1, G2 should be equal to composition of these two isometries, to pi of G1 plus f of G1 and pi of G2 plus f of G2. Okay, so let us compose it. So it will be pi of G1, pi of G2 plus pi of G1 f of G2 plus f of G1. Okay, so on the right hand here is the unitary part, here is the translation. So this should be equal to this. So we get that pi of G1, G2 should be equal to pi of G1, pi of G2, and f of G1, G2 should be equal to pi of G1 f of G2 f of G1, right? So the first relation means that pi is a unitary representation, and the second condition, maybe we still have this condition, right? It's exactly the way we've written the cocycle condition. Okay, so the second condition, okay, is exactly this condition. It means that f is in Z1. So the action of a group of a Hilbert space is given by a unitary representation and by one cocycle. Okay. Right. So we have, if you have action, you have this unitary representation and you have the one cocycle, and vice versa. If you have pi and one representation and cocycle, you get by this formula. The isometric action on this Hilbert space.
It must be 4 summand, not 3. F1, pi, Z2.
I made a mistake somewhere. Which were?
On the right side?
On the here?
Yes.
I think it's a right.
F, G1.
This is the composition. How you compose. So once again, the way it acts. So the way this isometry acts on a vector v. This is pi g v plus f of g. Okay, this is okay, and I think we didn't make a mistake. Okay, very well. So let us prove that once we translate it to this language, that this equivalence, okay, using this characterization that property T is equivalent to vanishing of the first cohomology group. So we'll prove. Okay, let us write. Okay, so proof. So we have right. Right. So we have to prove that if we, this is direct. If we have property T. If we have property T, then we have a fixed point, and if we have a fixed point, that we have the property T. So maybe we start by that if we have a fixed point, then we have a property T. Okay, so suppose that we have a fixed point. Okay, so that there is a vector v such that pi g v plus f of g is equal to v, right? It's a fixed point. But then we have that f, so f of g is equal to pi g of minus v, right? So it shows that f is actually in B1. Okay, so we proven that H1 is 0. Okay, and also the other way around. The other way around, if we have it's like it's exactly it's the same. So if we write f, so if h1 is 0, it means that f of g is equal. Okay, it's the same. Just I will write right. So it means that. So now the fixed point will be minus v, right? Okay. So it means that we have that pi of g minus v plus f of g is equal to minus v. Okay. So minus v is the fixed point. Okay, so as you see, this is just the change of the language. Okay, from translation from language of from cohomological language to the language of the action of the group. This characterization. So with each characterization, it's of course it's interesting. Just think about this. Characterization as a tool of proving property T or consequences of property T, but it also suggests some generalizations. Okay, so you have the action on the Hilbert space, but instead of Hilbert space, you could consider other spaces. Okay, and it makes sense to ask about fixed point properties for the action of the group on other spaces, and it's one direction of the research of trying to obtain stronger properties than property T, or just different ones when you talk about fixed point properties for the action on different manifolds. Okay, very well. Maybe one consequence of property T, which is related to cohomology that we will discuss now. Yes.
Question: where did we use that we have a Hilbert space but not any Banach space? Where did we use duality of Hilbert space? So duality.
No. So no, there are. So first of all, like here. So this was just like translation, this language of actions with this cohomological. So we just translated this vanishing of H1 to the language of H1. So of course you can develop this translation of the into different spaces. Okay, this is but what I want to. If you just about like now property T and you concentrate with like just with property T is equivalent to we have this equivalence. Yeah, it's just for the actions on the Hilbert space. Okay, we were in definitions. We were talking about unitary representation on the Hilbert space. Okay, so these are all like equivalences, and now I know your question is maybe if we could obtain other characters equivalent to property T. Okay, equivalent, but for other actions. Okay, so this is like this is separate question. It's a
no, we just can save the law.
Maybe isometry.
Yeah, isometry.
Right. So there are like two questions. It's whenever we're having some of these characterizations, you can ask about the equivalence in different setting, yeah, for different spaces, and some of them like you can really translate. They are equivalent. They give you some other properties, and then the other question is if you have this characterization for more general spaces, if it's equivalent to property T or not. Okay, and this is true that for just from property T you can obtain, for instance, this fixed point properties for also for other spaces. But I would it would require it would
that the fixed point property for Hilbert space for a loop is equivalent to have a fixed point property for the actual any bound space.
No. So I would need more time to describe what is known. Okay, but so you can translate this property of having fixed point bound spaces to other properties, but if you talk about O, but it's not equivalent to property T. Okay. Good. Maybe. Okay, so maybe briefly, can I, or maybe next time we'll discuss. Okay, so the one which is related to this cohomological characterization of property T, but can be it's a very easy consequence of property T is that so proposition groups with property T have finite abelianization. Okay. If not, if we had infinite abelianization.
What does it mean?
Pardon?
I don't understand what does it mean to have finite abelianization.
Finite. Well, what is the abelianization of the of the group? So this is the right. Right. Yeah.
Насильственно, значит, из группы делают табели таким насильственным образом.
А получается, конечно,
вот здесь, да.
Okay. Okay. So, and this we can easily see from the fact that Z, if it were infinite, okay, these groups are finitely generated, it would have Z as a quotient, and Z is infinite amenable group. So we have a unitary representation with almost invariant vectors and no non-zero invariant vectors. Okay. This is something that for a given group it's very easy to check if you have finite abelianization of naught. Okay. If you have, or if you have a homomorphism onto Z. This is actually to. However, we know that the proposition finite index subgroups of groups with property T have this property as well. Okay. So now, if we have any group with property T, it also implies that every finite index subgroup has a finite abelianization. Okay? This is called property FAB, and this is not easy to check for a given group. Okay? These are very, for many classes of groups, these are really deep questions, whether they have this property that finite index subgroup is has finite abelianization. So this is interesting, although it's a very easy consequence of property T. It doesn't sound as spectacular as this proof that groups with property T are finitely generated. However, this finite generation for a given group, you can very easily write a set of generators. However, proving that every finite index subgroup has finite abelianization might be very difficult, and in some cases this is the only way to prove it for a given group. Okay, so I think it's a deep consequence, and it's interesting to think about this. Okay, thank you very much.